the part of the resting membrane potential, in which we'll see that how the resting membrane potential eventually leads to the threshold potential. All right, so there are two kinds of summation: the summation of signals which lead to the touching of the resting membrane potential to the threshold potential, that is the 70 minus negative 70 millivolt becoming less negative to minus 55 millivolt. So the first category is temporal summation and the second one is spatial summation. All right, so in temporal summation there is one presynaptic neuron which continuously stimulates the postsynaptic neuron. So this is the presynaptic neuron, it continuously stimulates, so the signals add up and they summate, which is why we call it temporal summation, and it reach the threshold potential, that is minus 55 millivolts. The next category is spatial summation. In spatial summation, more than two presynaptic neurons, they simultaneously fire on the postsynaptic neurons. So there are multiple presynaptic neurons which are firing simultaneously on one postsynaptic neuron. So in this way, it directly touches the threshold potential. The resting membrane potential directly touches the threshold potential. All right, so these are the two categories. So now let us jump on directly towards action potential. So this is the most important category which we have to study. So how the nerve impulse travel throughout the membrane, this is the first important concept which we have to understand, and how the repolarization takes place. We'll see both of them one by one. All right, so first see that these are the sodium ion voltage gated channels, which are the most important category of channels responsible for action potential and depolarization throughout the neurons. This is the calcium ion voltage gated channels. Similarly, this is also the calcium ion voltage gated channels, and these two are voltage gated potassium ion channels. So suppose the resting membrane potential has touched the threshold potential. So after that, the voltage gated ion sodium channels will start to open, and the positively charged sodium ion will influx rapidly inside the cell membrane, and they will flip the script, that is minus 55 millivolt will turn into a positive 30 millivolts, and this is called let me write here, positive 30 millivolts is called action potential. All right, action potential. So when the membrane potential will become positive, this will move on to propagate towards the length of the axon terminal towards the axon terminal. And similarly here also, when it will reach minus 55 millivolts, then the voltage gated sodium ion channels will open, and the positively charged sodium ions will influx. So in this way, the depolarizing wave will travel throughout the length of the axon towards the axon terminal. Once it reaches the axon terminal, the due to the influx of positively charged sodium ions, the resting membrane potential will be changed. So the calcium ion voltage gated channels will also open, just like the sodium ions voltage gated channels, and there will be a rapid influx of calcium ions in the axon terminal. So due to which the synaptic vesicles which are located here, as this is the same thing which we'll discuss in the first lecture, that these synaptic vesicles which contain the neurotransmitters, and they have V snares, which are the hook-like structures which are located towards the terminal side of the synaptic vesicles. They will, under the high concentration of calcium, they will attach with the T snares which are located on the cell membrane, and eventually they will fuse with the cell membrane of the axon terminal, and the neurotransmitter will be released out. All right, so in this way, the V snares and T snares will combine together. The synaptic vesicles will come closer towards the cell membrane, and they will fuse to the cell membrane, releasing the neurotransmitter out of the cell. All right, and then eventually this neurotransmitter will stimulate the next postsynaptic neuron. All right, so now when the we'll see how the repolarizing wave travels backwards towards the length of the axon. All right, so there are voltage gated potassium channels which are located here, and once the depolarization has taken place, that is action potential is done, the voltage gated sodium channels will start to remove potassium out of the cell membrane of the neuron. And the potassium, since the potassium ions are removed, they will start accumulate the positive charge on the outside of the cell membrane of the neuron and creating the negative charge on the inside of the membrane, which will eventually, this negative charge will also lead to the closing of these calcium ion channels, which will eventually take back the synaptic vesicles backwards. And we have also seen that some of the extra neurotransmitter which is left here is also taken by the reuptake protein, which we have seen in the previous video. All right, so this is the basic concept of depolarization and repolarization and how the nerve impulse travels throughout the length of the axon. So now let us recapitulate all of the things which we have seen in a graphical format and understand two more important terms, which are the absolute refractory period and the relative refractory period. So this is the graph which I have drawn. This indicates the voltage here and the time here. All right. So this is the resting membrane potential minus 70 millivolt, and due to the temporal summation or temporal summation and spatial summation which we have already seen, the resting membrane potential will eventually touch the threshold potential, which is minus 55 millivolts. And after that, in this situation, the voltage gated sodium channels are closed, and once the resting membrane potential touches the threshold potential, the voltage gated sodium ion channels start to open. This is the activating gate of the, this one is the activating gate of the voltage gated sodium ion channels, which was earlier closed, starts to open, and the positive charge ions start to influx within the neuron cell membrane. All right, and this lower gate is called the inactivating gate, which starts to close once the threshold potential is reached. At the extreme point, that is at the spike of 30 millivolt, the situation is here, that is the inactivating gate is completely closed and the activating gate is opened. So now even if the positive charge comes here, it will not be able to cross the cell membrane since the inactivating gate is closed, and it will go back. So during this situation only, during this time only, the positive charge ions were able to influx inside the cell membrane. And now when all this process is done, when the cell has reached the action potential of 30 millivolt, after that it again starts to drop towards the repolarization takes place, since we have seen that the potassium ion starts to come out. So this is the repolarizing wave which takes the cell potential back to minus 90 in extreme situations when there is hyperpolarization, and which eventually restores out and comes back to the resting membrane potential due to the sodium ion, potassium ion ATPase pumps which we have talked about, and it will eventually restore to the resting membrane potential. So this is the complete cycle of the nerve impulse conduction and how the restoration takes place. So now absolute refractory period is a period from the touching of the spike of 30 millivolts to the period when it touches the resting membrane potential while repolarization. So during this period, the cell can no longer take the neuron can no longer take other stimulation, that it will not respond to any other kind of stimulation which will come during this period. So this is called the absolute refractory period, and this is the situation in which the cell completely cannot, because it is not possible to take any other stimulation. So that's why it is called absolute refractory period. And this period, when it restores from hyperpolarization to the resting membrane potential, this period is called the relative refractory period, because even here the cell is not able to take the new action impulses, but still it is possible, even if it not takes the new signals, but it is possible for the cell, because it is in the negative region, it is in the hyperpolarized state, still it is possible for the cell to take new signals, but the complete action takes place only after the resting membrane potential is restored. Thank you.